Okay, we'll get back to section 2.5 here. We're talking about continuity, and I've described the definition for what it means to be continuous at a number a. The limit as x approaches a of f of x has to be equal to f of a. All right, and I put a star by that statement. Make sure that you know that. We'll be using it all over the place for things in this section, okay, and even beyond that. And so we did a couple of examples, and right now we're looking at a theorem here. If f and g are continuous at a, and c is a constant, then c times f, f plus g, f minus g, f times g, and f divided by g are also continuous at a. Okay, g of a can't be 0 in the case of division. We know we can't divide by 0. All right, so let's maybe look at a proof of just the addition case. A proof of the other four operations would be very, very similar to what you see here. Now, since f and g are continuous at a, what does that mean? It means that the limit as x approaches a of f of x is the same as f of a, and the limit as x approaches a of g of x is the same as g of a. All right, so I'm going right to the definition. I'm going right to the starred statement here. Now, what do I have to show? I have to show that the limit as x approaches a of f plus g of x is the same as f plus g of a. Once I've shown that, then I'm done, because I'd be showing that f plus g is continuous then at a. All right, well, f plus g of x is the sum function, and by definition that means that you're adding f of x and g of x together. Now I know that the limit of a sum is the sum of the limits, right? So I can split this limit into two limits that would be added. And the limit as x approaches a of f of x, well, that's f of a, right? F is continuous. They told us that in the problem. And the limit as x approaches a of g of x, that's g of a. G is also continuous. But both f and g are continuous. We were told that in the problem. So I'm looking at f of a plus g of a. Well, that would be the same as f plus g of a. And that's what I had to get to, right? So this shows that f plus g is continuous at a. Now, the other three operations would easily fall out by using your limit laws. That's all I did here, right? Limit of a sum is the sum of the limits. Limit of a difference is the difference in the limits. Limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits. Okay? So these fall out because of our limit laws, essentially. Here's another theorem. Any polynomial is continuous everywhere. Well, a polynomial is a function of the form that you see here. A sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus right down the list. A sub 1 times x plus a sub 0. A sub n minus 1, a sub n minus 2, right down the list, down to a sub 1 and a sub 0 are constants. Okay? And now I want to show that any polynomial is continuous. Okay, so what does it mean to be continuous? It means that, again, this starred statement has to happen, right? So I need to show that the limit as x approaches a of f of x is the same as f of a. Well, the limit as x approaches a of a sub 0 is a sub 0. Limit of a constant is always a constant. The limit as x approaches a of x to the m would be a to the m, right? If you have a power function, you can make a direct substitution, and on every single one of these terms here, you're going to have something raised to a power. The last term is a constant. Limit of a constant is always the constant. Okay? So in doing that, you will be showing that the limit as x approaches a of f of x is f of a. Right? You can make a direct substitution of that a value into the function there. The following functions are going to be continuous at every number in their domains. Polynomials, we've already shown that to be true. Rational functions, radical functions, trig functions, inverse trig functions, exponential and logarithmic functions. Okay? Any function that you've worked with where the value is in the domain you can go ahead and make a direct substitution for that number in a limit calculation. Okay, now we've already used that a little bit. I kind of hinted at that, earlier in section 2.3, how I prefer that you make a direct substitution. Okay, it's less writing, and we're allowed to do that by our limit laws. Okay, well, I'm just kind of re-emphasizing that here. It's, I'm allowed to make a direct substitution by our limit laws. Let's take a look at an example here. So find the limit as x approaches -2 of x cubed plus 2x squared minus 1 over 5 minus 3x. This is a problem that we've already looked at earlier in the notes. If you were to flip back to that in section 2.3, you'd find this exact same example. Now the domain of this function would be all real numbers except for 5/3, right? I know I can't divide by 0. So if I were to, set 5 minus 3x equal to 0, I'd get x equal 5/3, and of course that's what I don't want. -2 is in the domain, right? 5/3 is the only number causing a problem in this function. -2 is in the domain. So if I wanted to calculate this limit, I can just make a direct substitution into the function. And that's what I've done. I've plugged in -2 into the function here. -2 cubed is -8, plus 8 is 0, minus 1 is -1, divided by 5 plus 6 is 11, -1 over 11, that'd be the answer. Okay? Let's take a look at another one here. The limit as x approaches 1 of arc sine of 1 minus the square root of x divided by 1 minus x. Okay, well, let's see. So we'll take care of the arc sine function in just a moment here, but inside the arc sine function, by the way, 1 is not in the domain of this function, right? There'd be a problem with division by 0, so this is not just a plug it in and you're done type thing like I did up here. Okay, we are not continuous at 1. Now, remember that what we were doing in section 2.3, I mentioned that when you're working with limits, most of the time it's going to be that you can't directly substitute in the number. Okay, this problem right here is easy because you can just plug in -2 into the function. Most of the problems are not going to be that easy. Okay, like there's going to be some work involved. You're going to need some algebraic manipulation there. Okay, so that's the plan, is can we algebraically manipulate the inside of this function to make a direct substitution. Now, I see this radical. We've done some things with radicals before in section 2.3, and the plan I had mentioned early on, if you can't make a direct substitution, you want to consider rationalizing the numerator or rationalizing the denominator. Now, the radical is in the numerator, so in this problem, I want to rationalize the numerator. To do that, I'm going to multiply the top and bottom by 1 plus the square root of x. 1 plus the square root of x divided by 1 plus the square root of x, that's 1. So there's no harm in doing what I'm doing here. I'm just multiplying the inside of this expression here by 1. That doesn't change anything. But when I FOIL the numerator, I'm going to have 1 minus x. The radical goes away. That's what I wanted. I wanted to rationalize the numerator. Okay. In the denominator, I just leave that as is. Okay. Now, 1 minus x can cancel with 1 minus x in the denominator, and that's what I've done on the next line here. I've canceled those. So now I'm looking at the limit as x approaches 1 of the arc sine of 1 divided by 1 plus root x. Okay, now at this point, there's no problem with making a direct substitution. I can plug in 1, and there's no issue like there was before. So I've done that. Lose the limit notation. And arc sine of 1/2, of course, I'd want to compute that value. I wouldn't want to just circle arc sine 1/2. So I need to figure out an angle such that sine of that angle is 1/2. Well, in a triangle, if the opposite side is 1 and the hypotenuse is 2, the adjacent side would be root 3, and the angle that you'd be talking about there would be pi over 6. I've drawn that on the side. And so pi over 6 would be the value of arc sine of 1/2, or sine inverse of 1/2 is pi over 6. Okay. Let's take a look at another one. Okay, here's a question. Where is f of x continuous? Okay. Well, let's see. So there's some different parts of this function that I'd want to consider in this question about continuity. I mentioned that, up here, the following functions are continuous at every number in their domains. Okay, so essentially in this problem, I would just like to know the domain of f. Right? Any number that is in the domain of f can be directly plugged into the function in a limit calculation. With ln x, I know I can't take log of 0 or log of a negative, so the ln of x would be continuous on the interval 0 to infinity. Tangent inverse of x is, here's the graph of the tangent inverse function. That is a graph that I did mention earlier in the review that I would like you to know. Okay, we will be doing stuff with the inverse trig functions. We will be doing stuff with the graphs. Okay, so this is one that you'd want to make sure that you know. This is the one that's got two horizontal asymptotes on it at y equal pi over 2 and y equal negative pi over 2. And the graph is in quadrants 1 and 3 as you see it approaching the two boundaries. The domain of the tangent inverse function is all real numbers, right? I'm covering the entire x-axis there, all real numbers. And then x squared minus 1 is a polynomial. Polynomials are continuous everywhere. I've mentioned that at the top of the sheet here, right? Polynomials are continuous everywhere. But x squared minus 1 is in the denominator, right? So I know I can't divide by 0. X can't be 1 or negative 1. Okay, so all in all, the function is going to be continuous on the interval 0 to infinity, but disregard 1 and negative 1. Well, negative 1 is not in that interval, right? So you're going to go 0 to 1 and then 1 to infinity. We want open parentheses there, open intervals, parentheses everywhere when we give our answer. So any limit calculation where you're using a number that is between 0 or 1 or bigger than 1, you can directly plug into this function here where you see x. Okay. The last thing in this section is the intermediate value theorem. I'm going to let IVT represent intermediate value theorem. Your book is going to do the same thing. And so let's talk about that next. Let f be continuous on a closed interval AB and n be a number with f of a less than n less than f of b. Okay, then there exists a number which we're going to call c in the open interval AB such that, st means such that, f of c equals n. Okay, here's a picture of what's going on with the intermediate value theorem. I've got a closed interval AB, closed means I'm including the endpoints there, and I've got some function going from A to B. Okay, now as long as the function is continuous on this closed interval A to B, then there exists a number c between A and B such that f of c is equal to n. Y equal n would be a horizontal line between f of a and f of b. Okay, so at some point, if you're going to start here at a f of a and go to b f of b, at some point you're going to have to cross this horizontal line, right? You can't jump over the line or do something like that. Otherwise, it's not going to be continuous. All right? Now, the value n that we're describing here can be taken on more than once. Okay? So here's a situation where you got a function that's kind of twisting and turning more. Here's a, here's b. Okay, here's y equal n. If I go from the point a f of a to b f of b, notice how I'm going to cross this horizontal line y equal n a couple of times, right? 3 times. So here I'm calling this C1, C2, C3, right? The value of n can be taken on more than once. The intermediate value theorem can be helpful in solving equations. So let's take a look at a typical example here. Use the intermediate value theorem to show that there is a root of the equation x cubed plus 2x minus 1 in the open interval 0 to 1. Okay, so this equation, by the way, would have 3 solutions. I know that from algebra because this is a degree 3 polynomial. There'll be 3 answers for x. Now, I want us to show that one of the answers is between 0 and 1. Now, I don't care what that number is. I just want to know that one of the answers would be between 0 and 1. Okay? Now, they're not asking me to solve this equation. Okay, that would be a very difficult problem, by the way, in algebra, because I unfortunately, to begin with the problem, I would have to guess and check. Okay, and that can be a very time-consuming, brutal thing to be guessing and checking, especially if I have no idea what the numbers look like. They could be oddball decimals or something that I'd never think of. Okay, so they're not asking me to, solve this. That would be tough. Okay, but just say that if I were to solve, okay, one of the answers would be between 0 and 1. Well, in order to show that, I can use the intermediate value theorem. Now, in using the intermediate value theorem, I need a function. Okay, so let's let f of x be equal to x cubed plus 2x minus 1. That's on the left side of this equation here. Now, f is continuous everywhere, since f is a polynomial. Polynomials are continuous everywhere, right? So, of course, f is going to be continuous on the closed interval 0 to 1. Be sure that you tell me that, okay? Since f of 0 is negative 1, okay, when you plug that number in, and that's a negative number, and f of 1, the right endpoint, when you plug that in, would return 2. 2 is a positive number. Then by the intermediate value theorem, there exists a number c in the open interval 0 to 1 such that f of c equals 0. Okay, now a root is the same as a solution or an x-intercept. Okay, and so if I plug in my 2 endpoints here on this closed interval, and on the left side I get a negative, and on the right side I get a positive, well, at some point I have to get an output of 0, right? There's some number c between 0 and 1 that will return 0. Okay, that has to happen. Here's a picture of this function. I didn't need a picture, okay, but just to show you what's happening here, we have this function. F of 0 is negative 1, so here's 0, negative 1. F of 1 is 2, so here's 1, 2. Okay, I'm drawing this curve, and if I start here at 0, negative 1 and go to 1, 2, at some point I need to cross the x-axis, right? I need to cross between 0 and 1. So whatever point that is, I'm calling that C0, okay? And that's what I had to show, right? I had to show that there is a root of the equation in the interval 0 to 1. Now, I don't know what that number is, okay? They're not asking for that, but, what we did here, this calculation would be very helpful in solving, okay? If I were to solve, like I already know that one of the answers is going to be between 0 and 1. So I have to begin by guessing and checking, that's my only option here. But at least I would have a place to start, like, start with using numbers that are between 0 and 1. Okay. Now, in a problem like this, there is some things that I would be looking for when I grade. Okay. I will see students mess this up, and they'll just simply say f of 0 is negative 1, f of 1 equals 2, and so f of c is 0, the end. Okay, I'm not going to give you very much points for saying that. Okay, first of all, what is f? Tell me what f is. Okay, we didn't have anything with function notation going on here. Tell me what f of x is. Also, none of this would be true if f is discontinuous. Okay, you have to tell me that f is continuous on the closed interval, whatever it is, a, b. Okay, that's something that I'm looking for when I grade, that you mention that f is continuous on the closed interval. Now, you have to state that it is a closed interval. If you say an open interval, Well, then you can't plug in these endpoints here. You can't plug a 0, you can't plug in 1 if you have open circles there. Right? So this has to be continuous on a closed interval. Then you can plug in your endpoints to see what the output is. Okay? So there's, more to it than just plug in this number, plug in that number, and f of c is 0 at the end. Okay? So be sure that you're careful with an explanation where you're using the intermediate value theorem. There's a couple of problems in this section where you're going to be using this theorem to show that there's a root of an equation on some interval there. Okay. We'll also use the intermediate value theorem a couple more times in the course for some things. Okay. So more on that later. But at this point, I'm done with section 2.5. Here's the problems that I'd like you to look at on page 124. Be sure that you've looked at the odd numbered problems there for me.